Hello everyone. I think we can start. Good morning, and this is the second part of the track around the dataset benchmarking and evaluating foundation models in EO. We follow on from yesterday's session for people that did not manage to attend. We had really nice presentations around benchmarking in general, on more, let's say, established way of doing benchmarking from GeoBench, Pangea, Filio. Then we also had some more innovative, different approaches around embedding space exploration from Hamed from Clark University, as well as in the Filio lab presentation, this concept of uncertainty around predictions for both regression and segmentation. And we also had one really nice presentation around building the right data set for pre-training from MMEarth. Today we have 6 presentations. We can start with the first one. That is from Adorni et al. From Arisa, and the topic is towards efficient RSFM benchmarking capabilities embedding approach. So I'll ask the speaker to come to the floor. Thank you.
Yeah, is it better? Yeah, thank you. I didn't see the button. So, hello everyone, I am Pierre. I'm a first-year PhD student at the University of South Brittany in the ESA lab, which is 50 years old this year, so we are very proud. And today, I will present to you my first contribution, which is quite different from what you may have seen yesterday, in that we use a novel method to benchmark remote sensing foundation models, which is called capabilities encoding. So as you may have seen yesterday, we have a lot of new papers describing foundation models in remote sensing, and we are especially focusing on vision foundation models. And so this is a little graph of many papers that came out in the last 5 years or so. And even though models have only gone better and better, as of today, there is not one model that can outperform all the others on every single task. So there is still a big need to kind of assess the strengths and weaknesses of each model and find out, which one are better for which task. So the classical approach that many works, such as those listed on the right, take, is to select a subset of the available downstream tasks that is made to be as representative as possible, and to fine-tune the models or train ahead on it, and test their capabilities like this. So we have many tasks with different task types, such as object detection, classification, etc. And we have many modalities. And this approach is good because it allows for a well-rounded overview of the model's capabilities, but we cannot assess the model on every single available task. So we have to make concessions and put aside some tasks, because it's not possible to fine-tune every model on every single available task. And so that is where we decided to work on. So our contribution is, as I said earlier, something we call the encoding model capabilities. So the goal of this method is to encode the model capabilities into a feature vector, such that we can have some kind of representation that allows for prediction of the model's capabilities based on just numerical values. So this is the rough idea. So we need to have some kind of latent space where different models that are displayed in space are positioned. And so our main objective is to predict the performance of a model on many datasets at once without fine-tuning it on these datasets. And also, as a byproduct of this would be to have a nice latent space to visualize the structure in a new way. So the intuition we had is if we could embed both datasets and models in a shared latent space, we could try to pull together or push apart models and datasets based on their actual fine-tuning results. So if we know, for example, that the model A is really strong on the dataset 1, we can pull these points together. And if we know that the model A is really weak on the dataset 2, we can push them apart in the latent space, such that models and datasets on which the model is good will be close together. And we have a well-organized latent space. So this is the intuition we have. So in order to realize this work, we needed to collect a lot of data. So we chose to use the GitHub repo, which is called Ocean Remote Sensing Foundation Models, which is made by, I believe, the authors of SkySense Foundation Model. And from this repo, we selected 36 articles, and we extracted the fine-tuning results of each model from the results section into a big table, of which you can see an extract on the right. And so this big table has 1,106 fine-tuning results from 85 models on 82 downstream tasks. So it is kind of a sparse matrix. We do not have a lot of data, but the goal is to try and fill in the gaps by predicting the values. So the first step in our method is to normalize the data. So what we do is, instead of trying to predict the actual values, such as, for example, the F1 score on this OSCD dataset, we will try to predict the position in the literature of each method. So the first step is to compute the distance to the best method. So in this example, the best method is SkySense with 60% F1 score. And the worst one is the ResNet with 48. So we compute the distance to best, which is 0 for the best model. And then we compute the relative distance to best, which is the kind of position in the literature, the relative position. So it is 0 for the best model and 1 for the worst model in the literature, which is called here delta. And then we can optimize our latent space. So what we do is we select a latent space that we choose. For visualization purposes, I chose the R2 space here. And we randomly initialize points using a Gaussian sampling. And we associate each point with either a model or a dataset. Then we compute the distance matrix between all the points in the latent space, which is on the bottom right. And we modify the position of the points using gradient descent with a MST loss between the distance matrix of the point and the actual ground truth relative position in the literature. That way, the distance between 2 points will tend to be equal to the position in the literature of the point corresponding to the model and the points corresponding to the dataset. So if we show what the process looks like, it looks like this, and we move around the points. And in the end, the latent space is more organized. So the first result is this latent space that was organized. And right off the bat, there are multiple things that we can remark. The first of which is there is a big cluster in the top right, which is the few-shot methods. So it's a little bit small, but there are many data sets here with maybe 5, 10, 50 samples. And the only models that are in this cluster are actually ConvNet and ResNet, basically. So it's kind of interesting to see that something that we already kind of knew is that the transformer is really better off when there are a lot of data to work with. Another remark we can make is, based on the way we optimize the latent space, it should be we should observe that the methods that are more general, that have better performance on average on all data sets, should be in the center of the cluster. That way they are closer to all the possible data set points. And it is kind of what we see in the middle of the big cluster. We can see methods with very good average performance, such as SkySense, for example. Our main objective was to predict the performance of the models. And so this is the result we have. We can predict the relative position in the literature by more or less 15%. And the graph you see on the right is, in the x-axis, the actual position in the literature. So 0 if it's the best method and 1 if it's the worst. And on the y-axis is the distance in the latent space. So we can see there is a clear correlation, so it kind of works. But we have really noisy data. And especially we observe that this prediction works way better when we have many points in the first hand to optimize the latent space. So for example, if we have a model for which we already have between 10 and 20 fine-tuning results, we have a better positioning in the latent space for this model, and we have a better prediction accuracy. So this method has some limitations. So the first goal was to reduce the need for fine-tuning. And we showed that it actually works, but we need a lot of fine-tuning in the first hand, so maybe 10 or 20 fine-tuning per model before we get accurate prediction results. Also, we predict the relative position in the literature, but we should aim to predict the actual MAP or reference score or whatever. And also, our ground truth is the results taken directly from the papers, but we know that different papers have put different efforts into fine-tuning their methods, so we know that it's quite noisy here. So to conclude, we propose a novel way of exploring RSFM capabilities that can allow for visualization of the latent space for providing insights for future research. And more importantly, it can be used to predict the accuracy of all models on a new dataset given, or the accuracy of all the models on a new, of a new model on all the datasets that are available by fine-tuning it only on a fraction of them. And so with more developments, this could become a good model selection method if, for example, we only have to fine-tune the model on 2 or 3 datasets, and then we have the results for all the datasets in the literature. It will be very interesting. So thank you for listening, and let's have any questions.
Are there any questions from the audience down there?
Yeah, thank you for the talk. Very interesting. Do you think that your method can be used to estimate trustworthiness of results?
Yeah, I have some kind of results for this. So on this graph, yeah, on this graph, we know that some points, which a point on this graph is actually a dataset fine-tuned on the model. No, sorry, model fine-tuned on the dataset. And I have plotted the individual points with the error. So I've seen that, for example, for some models, we have a very high error rate compared to others. And so it might be because maybe the authors of the paper have put a really big effort into fine-tuning their model, so we have very outstanding results, and the model cannot predict that. Or it could be because of trustworthiness issues, yeah. We don't really know, but what we did is some models that are really, really weird values, we just took them out in order for the optimization process to work. But yeah, it's kind of interesting. I may have some heat map of the errors with different models, and yeah, we can see some lines sometimes where it's really bad.
Okay, thank you. And another question, if I may. Are you planning to publish the resulting table that you have?
Yeah, so this paper was accepted as in a foundation model workshop for CVPR 2025. And we will be publishing all the data and the code, so it will be perfectly reproducible. I think actually it's already on GitHub, but the paper is not out yet.
Okay, thank you.
Okay. Maybe I have one more question, if I can. Yeah, can you expand a little on the fine-tuning? You said, that, for example, you need 10 to 20 run to make it reliable, but do you mean just to assess the variance, for example, of the errors and so on, or also you were meaning of trying, for example, different decoder, different hyperparameters, fine-tuning and search optimization, let's say?
Sorry, I'm not sure I understood.
Is the setup of the fine-tuning fixed, and the runner just to assess if the results are, there is a high variance or low variance or whatever, or you're also planning to change the fine-tuning setup to see if different decoder can work better on different encoders and other stuff like this? Thanks.
That would be very interesting stuff to research effectively, yeah. But I did not do any fine-tuning myself. So I just took the results from the paper, and it's quite, oftentimes the decoders are the same because in the literature everybody uses the same decoders. But yeah, as you said, it could be interesting to research if we have better results with some combination or... Yeah.
So just to clarify, the 10, 20 points that you need are based on results that others have published, and you're not actually doing any fine-tuning.
Yeah.
And I look at this similar to what they do in medicine with the meta-analysis, where they take results from different trials and they try to bring everything together, which is quite helpful. I have just, because we have a little bit of time for one last question, do you think that predicting with a delta of 0.15, something that goes from 0 to 1 most of the time, is actually reliable enough to make any decision beyond the ranking that maybe you get right?
So I don't think it's reliable enough to say 100% this method will be the best. But I think we can say that, okay, we have this group of maybe 10 models that are around the best possible delta. And so if you want to quickly go through the like 80 models that we have today and just select a few subsets that you can test actually with fine-tuning, it will be way quicker, I think.
Last question, how automatable is this method to actually gather all this data and make it something that can be constantly updated? For example, I could see this on Hugging Face or something, having something that, Yeah,
that's actually the goal. So the idea is now this was, actually, as you said, very passive. So we just took the results from other papers. But now we can take an active approach. And every time a new model comes out, we can test it on a few different data sets and just put the point in the latent space. And we can update the latent space interactively. And this would provide like a good overview of the literature, I think, in order for doing model selection later. So
that's great. Looking forward to see it.
Yeah, thank you.
Thank you. Can we thank our speaker? Everyone. The second presentation is from National Technical University of Athens, from Bontus et al. And the topic is on the generalization capacity of pre-trained uncertainties in remote sensing. The floor is yours.
How do I this clicking? How? Wow. I mean, it doesn't work. So should I click next to, but it doesn't move? Did I break it?
7.
So there is an uncertainty in our presentation.
Is that what that teach?
Okay, great. So I will obviously talk about uncertainties. I'm Nikos, and we present our latest work regarding the generalization of representation uncertainties in Earth observation. So, as everybody knows, in this workshop we have discussed a lot about multimodal foundation models in Earth observation, and we have seen impressive works that are able to excel in various downstream tasks, really capturing the nuances of the domain. And I was sitting one day with Spiros, and we were like wondering it would be really cool to have something really similar with uncertainty estimations. So we started kind of exploring the concept of a universal zero-shot uncertainty estimation. The main problem is that we have no idea how to approach this, and nevertheless, any idea whether this can actually work. So we started looking a bit in the literature review, and we found a really cool work by Kirchhoff et al. That actually tried to approach the concept of pre-trained representation uncertainties via a loss prediction task, which can act as a data uncertainty proxy. So the main concept here, I'm just going to describe it in a high level, no need for details. The main concept is pretty simple. You assume that you have a pre-trained model and a pre-trained classifier, for example, in BigEthNet. And all you need to do is take the representation space of a frozen backbone and train an uncertainty head on top of it to predict the loss of your training data. The uncertainty head is just a multi-layer perceptron, so it's really lightweight. You don't need to process the input image at all. You just cast your representation. And at the first time, all you need to do is just use the uncertainty head to extract your prediction of the loss, and this can act as your uncertainty estimation. So in this case, the backbone is actually irrelevant. It could be a vision transformer of any variant, or an actual flexible foundation model, let's say DOFA, HOMO, whatever, SkySense. So the potential of capabilities here is kind of infinite. So the main question is here, does it work? And if it works, what is the limitation, what is the potential, and how is it affected by the various nuances of Earth observation imagery? And as everybody knows here, Earth observation imagery is not like natural images. It typically operates in multiple scales. It covers various environmental conditions. And the concept of background is kind of non-existent. Every element can be considered as a class, as an object. So we have to if we really want to investigate the applicability of such representation uncertainties in the domain, we have to tackle the problem in each of these nuances. So we defined 4 semantic factors that shape this imagery, like ground sampling distance, that gives you the expected level of detail in the imagery, the domain of interest that gives you some thematic concepts that would exist in the imagery. For example, if you're operating in a marine environment, you would get different concepts than when you operate in the mountains. And similarly, the granularity of the targets, the classes themselves, would give you different detail in the semantic information that you will have, as well as the spatial arrangement, which basically translates to how the objects are placed in the image, which may uncover different processes that are underlying this image. And so, how can we imitate that? We created kind of a benchmark. We collected various datasets that cover the whole world, various ground sampling distances, multiple modalities, and we kind of tweaked a little bit some of the datasets to fit our experiments. We split the datasets in pre-training datasets and inference datasets, and some actually function for both, but we will see them in more detail. Now the question is, how do we actually understand whether these predicted zero-set uncertainties are actually meaningful? Intuitively, representations that have lower uncertainty should be accurate. We are very certain about these representations. At the same time, inaccurate representations should exhibit high uncertainty. The question here is, what is actually accurate representations? We are really familiar with accuracy in the classifier layer. We can just take F-score, accuracy, whatever, but the representation space, it's really vague. So obviously, we're not the first that had to tackle this, but people in the literature typically use recall at one. Recall at one is basically a binary metric that assesses two nearest neighbors at the representation space and checks whether this belongs to the same class. If they belong to the same class, then okay, our representations are really accurate. If we want to translate that to an uncertainty quality estimation, we can just compute the ROC between the predicted uncertainty and this accuracy. The problem is that recall at one operates at multi-label, at a single label, and the transition to multi-label setups and semantic segmentation setups is really abstract. So we have to deal with it before going on with our investigation. And I'm really out of time. So I'm gonna go a little bit fast on that. What we had to do is extend recall at one. For the case of multi-label classification, this naturally derives from the single label class. We just have to tweak a bit the concepts. Like, what I really want is to have at least one class in common for the two samples to be considered close enough, or have all of the classes to be common between of them, or the percentage of them, or something like that. For the case of semantic segmentation, this becomes more complicated because sharing the same class is not as straightforward as it would be in single label classification or multi-label classification. The problem is that each area may have a dedicated class, and you only have one representation. So we define various metrics that try to cover two distinct types of similarity, spatial and contextual. The spatial similarity would basically tell you that if in the same area you have the same class, then your two samples are really similar. But that would mean that you have a lake in the top left corner and a lake in the bottom right corner, and these are not similar. In the contextual kind of approach, these two samples are similar. So we kind of create metrics that encapsulate both, either independently or combined. I will not bother you with the exact metrics because it's too much work, but you can look it up in our paper. So let's dig in a bit in the investigation and what kind of insights we get. We got. No. Okay, yeah. So don't focus too much on this graph. It's really complicated. So I will just give you the overall description of how this investigation goes. We pre-trained on 4 different datasets: ImageNet, an optical task, BiggerNet, FLAIR, and a variation of BiggerNet that basically aggregates some classes to imitate a lower granularity in the targets. So this plot is basically the performance of each pre-training sim at various downstream tasks for all of the metrics that we presented. So I will guide you through our main insights. The most clear one is that EO pre-training actually produces reliable uncertainty. So all of the metrics consistently outperform the image pre-training and also the random baseline. So we're really good at that. Importantly, it is also robust to domain drift, and this can be seen in the MARIDA dataset. MARIDA is marine debris detection dataset, and all of our pre-training datasets mainly come from land cover classification tasks, and even in different geographical locations. So we're really robust to a drift of concepts that we expect to see in the Earth observation imagery, as well as to the variability that is induced by a change in geographical location. Now you may wonder, okay, what do I do with that? Let's test it in the real world. To do that, we utilized a BigEthNet dataset and a subset of it that is typically excluded during training that mainly contains clouds, snow, and shadow. With the hatched bars, you can see the prediction, the uncertainty estimation for the noisy part, and with the clean rectangle, you can see the uncertainty estimation of the clean dataset. Blue refers to pre-training in FLAIR, which is a land cover classification of high resolution in France, and with orange on ImageNet. What I want you to take away from here is that after the FLAIR pre-training, we see a drop in the uncertainty when we have the clean dataset, which actually reflects the noise that we expect to have when we have clouds, snow, etc. On the contrary, ImageNet pre-training results in higher uncertainty in the clean dataset than the noisy one, which doesn't really make sense, and it actually reaffirms 1 minute. Okay. So I will just give you the brief overview of our overall results. We're also really robust to the concept granularity, which means that in the pre-training case, we may have coarser labels, and if we go to the downstream class with a more high resolution labels, it's the same thing as if we had high resolution labels at the pre-training. Similarly, the ground survey distance at the pre-training affects the generalization of our certainties, meaning that high resolution pre-training is more reliable for high resolution downstream tasks. And it is ideal if you try to align the resolution between the pre-training resolution and the downstream resolution. So even for lower ground survey distance, you would ideally require lower resolution pre-training. So, a fun fact, these zero-shot uncertainty estimations actually align with task-specific learned uncertainty estimation. This is really important because we have no information for the downstream tasks whatsoever at the pre-training. You can have whatever downstream task you want in your mind, and typically it aligns well with our estimation. However, aggregating the uncertainty into one value does not make much sense in Earth observation, since we typically operate at pixel level, one of the last slides. But it's really important. So this is a really restricting limitation in the current approach that we currently have, and we wanted to go beyond that. So we kind of tweaked the transformer architecture, taking into advantage the sequential nature it has. And we considered each patch of the vision transformer as a special area in the Earth observation imagery and tried to extract the uncertainty of each location independently and produce the uncertainty map of it. I'm closing with this. So these are the results, and they are compared with the downstream loss, which can be considered as a proxy of the uncertainty. And fun fact, the clouds in the MARIDA dataset are predicted with high uncertainty, and the snow with high uncertainty at all. So next step, improve spatially aware uncertainty estimation and really move towards a universal, flexible, multimodal, zero-shot uncertainty estimation and other buzzwords. Thank you for my attention. And some examples, if you will, like low uncertainty uncertainty.
Any questions from the audience? There's one down there. Okay. What? Eisenberg tall.
Thank you for your talk. I was just wondering how this uncertainty relates to other uncertainty measurements that you can do, like from Candle or what you do in regression, right? You can directly learn it. What you now do is somehow predict the loss uncertainty already, but you can already learn an uncertainty term that's directly coming, it can be included in your loss function, right? So instead of predicting just your class, you could also predict, or your regression target, you predict the uncertainty directly. And I wonder how this just relates to one another.
So you mean when I'm training for a task, I can also extract the uncertainty of the prediction, even though I get the class. The problem with that is that it's task specific. So I have to do it every time I have another task. The question is, how do I generate it?
All right.
It's like, I mean, if you have a very specific task in mind, you're already working on that, the ideal scenario, even in foundation models, just do supervised. But if we want to go through something bigger from the generalizable, you have to look for other ways. And it's still initial work. Just to clarify, this work was mainly to understand the limitations, and we have something that's bigger in our minds. But it's really valuable to put a stop at some point and just think, okay, what does it work? What do we need to do for the domain, et cetera, to build on that.
Okay, cool.
In the interest of time, we'll move on, but available in the coffee break for more questions.
Sorry for abusing your time.
No, that was really interesting. Thank you very much again. So the third presentation is Gaia, a global multimodal, multiscale vision language dataset for remote sensing image analysis from Zavros, University of Athens. The floor is yours.
Yeah, so good morning, everyone. As of today, as you know, Earth observation satellites are generating an unprecedented amount of data. Europe's Copernicus satellite mission alone generates more than 20 terabytes per day, which, as a matter of fact, outstrips our capacity to extract meaningful information from those data and interpret everything. At the same time, we are currently witnessing a paradigm shift with the introduction and the adaptation of vision language models, which changes the way we interact with those data and help us via natural interfaces and primarily language to interpret those data. However, there is a critical problem. Most of those existing VLMs are trained on web data, which are general purpose and are not sufficient for remote sensing downstream tasks. So today we are trying to mitigate this issue, introducing Gaia, a global multimodal, multiscale vision language dataset for remote sensing image analysis. Okay, but before delving into our dataset, let's understand what the language has to offer to the problem at hand. So language offers an efficient but lossy encoding of concepts, which enables our models to learn more abstract representations and converge faster. Nevertheless, sensory experience is also crucial for real-world understanding, since language alone misses vital physical world knowledge and properties. So why don't existing datasets solve this problem? We could split existing VLM datasets for remote sensing into two broader families. So the first family of datasets contain RS-tailored image text pair datasets, which are often small scale and manually annotated, which is costly and slow. At the same time, they focus on specific resolutions and modalities, which is usually very high resolution aerial imagery and RGB modality. And some recent efforts to create large-scale datasets with automated pipelines are based on class labels, like, for example, taking bigger net classes and forming sentences that describe the image, or using the OpenStreetMaps labels to form descriptions. The other family of datasets is web scraped data. We don't have many works like this in remote sensing, but the few that already exist are trying to filter existing large-scale datasets from the general domain, like Lion, and filter them for remote sensing samples. For example, in this work with Lion.io, they filter a 5 billion image text pair dataset and derive approximately 100,000 samples. We can see some of those samples below in the image. We can see that the images are of sufficient quality, but the captions are short, noisy, and they do not contain the remote sensing expertise we would like to train our models on. So this is where Gaia comes in. The main features of Gaia is that first of all, its scale. It features 41,000 RS images featuring 5 diverse synthetic captions that we generated, in addition to the original alt text caption and the metadata that we web scraped from the internet. The thematic focus, it encompasses phenomena covering all major 5 Earth spheres, as you can see on the side. And it exhibits minimal overlap, less than 3% with existing web-crawled datasets. So about our construction pipeline, as I said, we web scrape remote sensing articles. We have discovered several repositories like the ESA or NASA image galleries that feature articles with one main image and big chunks of accompanying text that describe the image itself. Independently from the source website, all articles contain the main image, as I said, and the accompanying text with some also RS-related metadata like sensing date and location. So after the web scraping, we clean up those data and deduplicate them, and then we use ChatGPT 4o, the multimodal model from OpenAI, to annotate the remote sensing image with 5 diverse captions, conditioned on the text article that we have already scraped, so that we are sure that our captions are true and we don't introduce any hallucinations to the generated captions. We also fill the metadata missing from the article. Maybe the location, for example, is missing, and we can fill those missing information with information extracted from the text itself. So we can see one sample, one web scraped sample. So we have the original image, it's a SAR image. We have the original alt text, which, as we already told before, fails to provide enough information about the image. In this specific case, we have only the date of the capture date of the image. And next, we see the synthetic captions we generated. Just for your information, this image is accompanied with a 500 words article. So we have enough information to derive from the article and produce captions with enough diversity. I have with bold text some of the main attributes of the captions, like the toponyms, the type of the image, the main observation, and like secondary observations outside of the main concept of the image. So regarding the spatial distribution, you can see all three stratified splits, the train, test, and validation, which have been spatially and temporally stratified. And we also incorporate some oftenly underrepresented areas like the Arctic. Now, regarding the temporal distribution, our dataset spans more than 25 years, starting from 1998 and reaching up to the end of 2024. We have also relatively uniform distributions of observations across all months, so it's pretty balanced in this way. Now, regarding the sensors, modalities, and the resolutions, we feature more than 120 satellite missions and images from various scales and various modalities. Now, regarding the textual richness, we can see that the synthetic captions provide far richer and more detailed and diverse semantic descriptions, with high lexical diversity and moderate semantic diversity. We have measured those two factors with metrics like HDD for lexical diversity and also the semantic diversity. So, two quick examples from our BLIP2 fine-tuned model. I won't bother you with any tables with metrics. You can see them on the paper I will share on the last slide. So we have on the top the main alt text, which is web scraped, one of our synthetic captions, and then we have the zero-shot prediction of the BLIP2 model, and then the fine-tuned BLIP model prediction with alt text in the beginning, and the last one is the synthetic captions fine-tuned BLIP2 model. We can see the big difference in detail and also some misinterpretations with the zero-shot and the alt text fine-tuned models. Same output here, same observations. The synthetic fine-tuned predictions are more realistic and closely related to the domain. Now, summing up, we introduced the Gaia dataset, also the automated annotation framework for containing the ChatGPT prompts and the structured output schema to extract the relevant metadata, also the pre-trained models, and some future directions. We aim to scale up the dataset with more internet sources, enhance the annotations with dense captioning, especially now with models, especially the open weight models, being more affordable compared to the ChatGPT, where you have to pay for the API calls, and add the complementary modalities for each sample. So we have diverse inputs, use more sophisticated VLM architectures. For example, BLIP2 do not use a location encoder. We would like to have one in order to be more precise and see how it improves the output of the model, and perform some broader evaluation in order to have more realistic downstream tasks like, for example, biomass estimation and other more relevant downstream tasks. So thank you. This is the QR code of the paper. You can see more details there, and also the GitHub repo and the Hugging Face repo.
Thank you very much. We have time for one burning question. Yeah.
Thank you for your presentation. Just a quick query. Is my understanding right that you web scraped the remote sensing articles, right, from across the world and then prepared this data set? Now the query over here is, it all depends on the events that has happened in a place, and then articles have been published. So in terms of multi-temporality, for a single place, there is a big chance that you do not get another article of the same location for any other year. So how did you cater that?
Okay, so if I could move back a little bit. Okay, so we have used specific tiles. We used GeoHash in order to provide for the same area in the globe enough art samples covering both the temporal and the spatial aspect of this tile. So we cannot guarantee that for a specific location we have all 4 seasons, for example, but from what we have observed from our exploratory data analysis is that usually we have nearby locations, so we expect the semantics to be related. So it's, especially if we move to this one, it's pretty dense coverage. So I think that for sure you won't have the exact same locations. It's not guaranteed for all 4 months or 4 seasons, sorry. But yeah, within the tile you will have for sure enough coverage. Thanks.
Thank you very much again, and he will be available during the coffee break. I think it's just me.
Okay, so the next presentation is evaluation of cross-domain generalization capabilities of remote sensing foundation models. Yeah, Julia, the floor is yours.
Thank you. Good morning, everyone. So I'm a postdoc researcher at CNES, and this work is part of the IRMA project from Saint-Exupéry Research Technological Institute. And so this is a study on how foundation models can or cannot generalize to a different domain, and especially to a different sensor. So let's start with some background. So here we consider as foundation models the vision transformer encoders that have been pre-trained on multiple sensor datasets. And then they produce representation that are used for a large range of downstream tasks. And since the annotation is very costly, usually the small-scale datasets only cover a single sensor. So the question that started this work is the following. Can we imagine that we have a final model able to solve a task that was trained on a single sensor, but that can still be applied to different sensors as inputs? So why would we want such a model? Well, we do have a lot of archives, a lot of data available, and since the common practice nowadays is to annotate small datasets for every new sensor and every new task, we actually have a lot of small annotated datasets. So it would be great if we could just use whatever dataset is available and annotated for this task, regardless of the sensor, and then be able to apply the final model to any sensor. And then the other advantage would be that we will have a single AI model to be applied to any future sensors, and so we would reduce the cost and the time to produce new applications. So this study is a first step towards such a model by evaluating state-of-the-art models in a cross-sensor scenario. So first we consider a change in spectral bands and spatial resolution for optical images with the first use case on marine object segmentation. And then we consider a change in sensor modality between optical and radar images with a float segmentation use case. Okay. So let's talk about the methodology. Here we consider those 5 foundation models. So they all use the VIT-based architecture, but they were pre-trained with different data sets, different training methods, and they use different input modalities. So the only exception here would be remote clip, that is not technically a multi-sensor model, but since it uses only RGB images as inputs, it won't be affected by the change in spectral bands, so that's a good reference to have. Then all of the experiments were performed within the Pangea framework. So the models were frozen, and then a UPNet segmentation decoder was trained using a supervised dataset. So for the first use case, marine object segmentation, we compared all of these models and also 2 fully supervised baselines. A unit also trained in Pangea, and then the Marinext model, that's a CNN-based encoder, and the SegNext decoder that was already trained for this specific use case. And then for the second use case, we needed a single encoder pre-trained on both optical and radar images, so we had to focus on DOFA and Galileo models. And all of these models were already implemented in Pangea, except Galileo that we have added for this study. Then for the datasets, so for both use cases, we needed a source dataset for training and 1 or multiple datasets for evaluation that we call the target dataset. For marine object segmentation, we used MADOS as source datasets. So those are Sentinel-2 images with 15 different classes of marine objects and also different state of the water. And then we used the first target dataset, that is NASA Marine Debris dataset. It's composed of PlanetScope images with only RGB channels. And here we have a few marine debris, but also natural floating objects annotated with bounding boxes. And finally, we used a much more difficult dataset that is from Worldview 2 images with different categories of ships annotated. So here the spatial resolution is 50 centimeters, so it's very different from the 10 meters from MADOS. And then for the second use case, we used the common SEN1 floats dataset that is annotated with water and not water pixels on both Sentinel-1 and Sentinel-2 images. So here we will train the model using only one of the modalities and evaluate on the other. Let's have a look at the results. So for the first use case, the first thing we did was evaluate if the models had learned the source classes on MADOS. So here's the mean IU that was calculated for all models. And the first thing we can notice is that both supervised baselines actually perform better than foundation models. But here we have to keep in mind that those foundation models were pre-trained using terrestrial images and then frozen, so they didn't get to learn specific ocean features, unlike UNet and Marinext. And then we have 2 drawbacks with the dataset that are a bit hidden here that we don't see in this metric. The first one is that the classes are very imbalanced, and so are the IUU for every class. So even though DOFA, Remote Clip, and Spectral GPT seem to have the same performance, they actually perform very differently depending on the class. So if we want a more thorough understanding of the performance, we need to have a look at the specific classes. And then the second drawback is that here you can see the annotations for this dataset, and those are only the red and the pink pixels here. So we only have a few objects annotated in the images, so we don't really know what's happening around those annotated pixels, and the metric only reflects those very few pixels. So for the remainder of this presentation, I will focus on showing you a lot of segmentation maps that are produced by these models. So here's the first example. We can say that the segmentation map from UNet is correct. However, for DOFA and Remote Clip, the annotated pixels are correct, but the segmentation do not respect the boundaries of the objects. So depending on the final use case, the segmentation maps might not be satisfying. So here, the UNet would be the best model. And then for Galileo, although it's the most recent model, here we can understand why the mean IU is so low compared to the other foundation models, because it does a lot of classification mistakes compared to the other foundation models. However, to do it a bit of justice, when it does have the correct class, The segmentation map is much more similar to the UNet one, so it actually improves over other foundation models, and that was the point of its specific pre-training. So here, both UNet and Galileo produce very good segmentation map, although for Galileo, it is better on pixels that are not counted into the mean IOU. Then let's have a look at two classes that are of interest for the generalization case. So first, the marine water class is sort of the background class. So when we do have ocean water without any object, without any perturbations, all the models are very good at identifying this class. And then we have, on the opposite, the marine debris class that is, the annotations look like this. So those are the pink pixels. So we can see that here we have 3 debris. We can see there are a bit more of those, but they are not annotated. And again, UNet produces a very fine, very good segmentation, while DOFA and Remote Clip have the annotated pixels correctly, but it's, again, they go way beyond the objects. And Galileo only sees one of the annotated objects. But those are classes that are of interest in our target dataset, the NASA marine debris. So here we have a few of the MADOS classes that are actually considered as marine debris in this second dataset. The images look like this, and the segmentation maps that we obtain are as you can see here. The first thing to notice on the first row for UNet is that the UNet doesn't recognize anymore the marine water class that was the background. It often associated with the sparse floating algae class, so it basically sees algae everywhere on the images. And then for all of the models, we can see that they do segment some objects, however, they're not able to correctly classify them. So the best model looking at these images and also many more would be DOFA, because it is the only one that sort of recognizes the background and also some of the algae, some of the floating objects, but it's very far from being satisfying. So here, none of the models has been really able to generalize to this new sensor. And then if we look at the ship class in MADOS images, so in the source images, all of the models are able to segment this particular object. And here we can see that it's actually Remote Clip that obtains the best performance for this class on the entire test set. And then when we apply the same models on the GeoFi ships dataset, so these are much bigger images with a much higher spatial resolution. On a very small ship like on these images, we can see that UNet, DOFA, and Remote Clip sort of segment objects, but only Remote Clip associated with the ship class. Although the total IOU on this new dataset is only 2%, so it's, again, not satisfying. However, DOFA also recognizes correctly the marine water background class. Then here's another example where we only have one of all the little ships correctly predicted. And finally, when we look at much bigger ships, the models do not recognize them as single objects. So quickly for the second use case, here we trained models on a flood segmentation task using, in this case, Sentinel-1 images. And then we applied those models on Sentinel-2 images. If we look at the IOU for the water class, we can see that there is a slight drop in the performance, but it's actually not that bad. We don't drop to 0 like it was in the previous case. However, in the other way around, so we train on Sentinel-2 images and evaluate on Sentinel-1, the drop is much, much bigger. And here we can see a difference between DOFA and Galileo, where DOFA drops from 80 to 8%, while Galileo only drops to 40%. So we can say that Galileo, he does generalize better than DOFA. However, it's still not enough to call this a good generalization to the new sensor. Here's another example where we obviously see that whatever the training modality, both models tend to predict more water pixels in the Sentinel-2 image. Now to conclude quickly, so we have seen that the foundation model is not naturally generalized to different sensors, even though they have seen some of the characteristics during pre-training. We can say that the latent spaces are not sensor agnostic, even when we try to put the different sensor representations together, as we did with Galileo. And also, if we want to pull all sensors together, we need co-registered images for all sensors, and that might not be possible for any satellite or any modality. So how could we improve this generalization performance? Well, first we could work on the supervised training phase. We could use more tasks at the same time. We could use more data sets, which are methods that have been very effective for the pre-training step. And then since the latent space seems to be very important for the generalization of the models, maybe we could start thinking about building a more meaningful latent space as soon as the pre-training strategy. Thank you for your attention.
Thank you again. Thank you for the talk. It was very interesting. I wonder, have you looked into domain transfer papers that try to be agnostic to certain things like domains, right? For example, there are some papers that use, discriminators to say, okay, we would like to not correlate with, for example, years, and then they decorrelate so that you cannot recover the signal. And I wonder if that's something maybe one could try here, or do you know about this? Might this be, interesting?
So far, this was just so what's happening with current models, and then maybe some decorrelation method would be very useful, but that would be in the pre-training step, because it's when building the latent space we will want to decorrelate the content of the images with the sensor styles. So that would be a possible direction.
All right.
If I understand correctly, for the foundation models, you use the embedding and then you train a decoder. Which is the size of this decoder with respect, for example, to the supervised unit?
I don't remember exactly. It's the UPNet decoder, so it's the one used by default in Magellan and also many papers. So it's supposed to predict very good segmentation, but I haven't checked exactly the size of it.
The question is, if the size of your decoder is more or less the same size of the supervised unit?
I think it's more or less the same size, because in training it took about the same size.
What is the interest of using a foundation model if what you have to train has the same size that the fully supervised model?
Well, it's for the generalization, because the unit, if the supervised model only sees one sensor, it will not be able to generalize to more. Whereas in our case, the foundationers have seen, we consider that they will see enough sensors during the pre-training phase to then be applied to other sensors without seeing them in the supervised training phase.
Okay.
Okay, so we will move to the next presentation. Okay, so the next presentation is 40, a benchmark for forest type mapping and geospatial foundation models by Xiang et al., University of Zurich.
Okay. So hello, I'm Yu Chang from University of Zurich, and I'll present 40, a benchmark for forest type mapping. This is actually the internship work that I done at Google DeepMind, and together with Maxim Neumann.
Yeah.
Okay. So first of all, let's talk about forest mapping. We know that there are already many amazing works about forest maps, and usually they focus on answering the question, where are the forests? For example, they typically use the definition, forest means trees higher than 5 meters and canopy cover more than 10%, which means they focus more on forest coverage, so distinguishing forest from non-forest areas. And here we want to go one step further. Besides asking the question where, we want to answer what kinds of forests there are, because not all the forests are the same. And as you can imagine, here like natural forest, planted forest, and tree crops, they are quite different in biodiversity, carbon storage functions, and maybe other ecosystem functions. So having this kind of detailed forest type map can help enable the better deforestation risk, degradation monitoring, better biodiversity monitoring, and also support for the EU deforestation regulation. And that's why we want to propose this deep learning benchmark for forest type mapping. And now let's talk about this dataset. In general, this is a global scale, multimodal, multi-temporal deep learning benchmark. And here, as you can see in this figure, we try to sample globally, and we get 200,000 samples. And each sample has a coverage of 1,280 square meters, and they are at 10-meter spatial resolution. They are also annotated with per pixel labels, means they can be used to train the segmentation models. And for the classes, we have 3 forest classes, natural forest, planted forest, tree crops, and we also embed some non-forest classes, other vegetation, built, water, ice, bare ground, just to enrich the segmentation labels. For our reference data, we try to collect and merge many diverse publicly available data sources. And here I list some main data sources that we used. For example, we use world cover to get labels for some non-forest classes. And we use primary humid tropical forest to construct the labels for natural forests. And for tropical moist forests, we use different layers in this database in order to get labels for both natural and planted forest. And for this spatial database of planted forest, we use its labels of planted and tree crops to construct our own labels. And of course, there are many other data sources that we use, but not listed here. For example, we use some regional databases of tree crop species like maybe cocoa in Africa or palm in tropical area in order to get more tree crop labels. In the end, we use those public data sources to construct the rich labels in our data set. And for our input data, we combine different satellite data. So we have Sentinel-2 and 1. They have 10-meter spatial resolution, and we extract the data in 3 years, from 2018 to 2020, and we have provided the mosaics in 3 temporal settings, so monthly, yearly, and also seasonal. We also provide additional data such as climate from Terra climate and also elevation data. And here are some data samples in our data set. And as you can see, we have quite good segmentation labels, although there are some still black areas. In those areas, they are the non-label areas. And we geographically split the dataset into training, validation, and test area. And we try to explore the class distribution in these datasets. In general, we try to balance this class distribution at the image level during the sampling. But as you can imagine, it's very hard to make it perfect. And this is an image we can show here. This is a distribution of class at pixel level. It's quite clear that the majority pixels are from other vegetation. And as for the forest classes, we can see that fewer pixels are from planted and tree crops. This is because, first of all, it's quite hard to collect a data set for those 2 classes. And usually they just cover a smaller spatial extent. But we believe that this kind of distribution can reflect the reality, and we hope that further research work can dive into this imbalance data problem and help solve the real applications. And this is another analysis. So here the figure shows a number of classes within one single image. And as you can see, most of our samples contain at least 4 different classes within one single image. This means this is quite good to train a deep learning segmentation model, as you have enough classes within one label. Yeah. Now let's jump to the model part. So besides the dataset, we also try to develop a model for this forest typing forest type mapping task. And we call this model multi-model temporal spatial vision transformer, MTSVIT. So in general, we try to process different modalities, for example, Sentinel-2 and 1, into tokens separately, and then they go through the shared spatial encoder and temporal encoder in order to generate the spatial temporal features for each modality. And then inside this multi-modal decoder, we let different modalities interact with each other in order to get the final features and then go through the segmentation head to generate the final prediction. Yeah. So now I'll present some results. Here, for this experiment, we use seasonal Sentinel-2 climate and elevation from 2020 as inputs, and we compare our model with UNet3D, UTAE, and TSVIT. As you can see in this table, we try to show the F1 score for all the classes and also for different forest classes. In general, we can say that our model is the best across all the metrics, and especially in the imbalanced data part. For example, the P and TC means planted and tree crop classes. And also inside the bracket, there are the standard deviation across repeated runs. And this also indicates that our model is quite stable across runs. And another thing to notice is for this TSVIT, actually this is the foundation of our model. And as you can see, this is the second best in this experiment. The main difference between this model and our model is the inject of our multi-modal decoder, which means using multimodality is quite important for this forest type mapping task. And besides this another thing to notice is we are also doing evaluation with more geospatial models, and those evaluation results will come later. Yeah. Besides these experiment results, we also do some ablations. One thing is the multimodality ablation. So here we use our proposed model as a baseline and try to check different kinds of inputs combinations. For example, Sentinel-2-1 elevation and climate. And it turns out that the best combination is from Sentinel-2 elevation and climate. And it seems like Sentinel-1 is currently not that helpful in this task. Yeah. Besides the multimodality, we also conduct the multi-temporal ablation for this task. So here we use all the temporal settings in our dataset, the seasonal, monthly, and yearly data from different years to run this task. And it's quite clear from this figure, using seasonal and monthly data can largely outperform just using the yearly data. And also the performance gap between using seasonal and monthly data is quite small, which indicates that, yes, temporal data is quite important for this task, and especially the seasonal patterns. Okay, so let's summarize. This is a global scale dataset containing 200,000 samples, and we have multiple modalities and also multiple settings of temporal time series. And we hope this can serve as a test base of geospatial models and contribute to more forest-related applications. And here I show two examples in our group. So we already use this dataset to contribute to generate a high-resolution tree crop map for South America, and also a natural forest map for the whole world. And currently they are under review. Yeah. So this is the end of my presentation, and please stay tuned to our work. Actually, we are open source everything, almost everything. So for this benchmark, the dataset is already released on this GitHub page for its typology. And also we are preparing more evaluations on the geospatial foundation models. And as for the code framework, we are releasing two code framework. One is Geo. This is a JAX-based machine learning framework for Earth observation. And the model I mentioned, MTS-VIT, its implementation is already inside this GitHub. And also for Gflow, this is a very efficient package to help get the satellite data or other data layers from Google Earth Engine and pack them into TensorFlow datasets. So you can directly use that for your training. And also for application and maps, our works are currently under review, and we have planned to publish those maps upon the acceptance. Yeah, and yeah, that's it. For now, we don't have a unified webpage to include everything. But if you are interested, please follow my personal webpage, and I will try to update all the news on my page. Yeah, that's it. Thank you.
Thank you. That's really cool work, really necessary. Can you talk a little bit about the difficulty of getting the labels for the tree crops? You mentioned cocoa and Ghana. That's super hard. How did you do that?
Yes, I agree that it's super difficult to get all the labels, especially for the tree crops. And so in our case, we try to gather all the public data sources that we can have. And as you can imagine that there is no unified data labels for everything. So we try to collect, for example, cocoa from Africa and some other tree crop species from America. So it's quite distributed. And in this current version, that we can now say that we already include everything in our data labels. And we are actually planning to collect more and more data, not just from the public available data, but also maybe from other smaller organizations in order to enrich the labels. But in general, yeah, I agree. This is the most difficult part in this project, actually. Yeah.
Thanks. Cool talk. Very informative. I was wondering, there are some other 10 meters land cover products, right? Like, how does your product or data set sort of compare? Like, can't you just use ESA world cover, or like, why is that much worse?
What do you mean? You mean instead of world cover using other dynamic world?
No, world cover also has trees, obviously, as one class, for example, right? Like, how is your data set? Is it a lot more accurate, or like, well, what's the difference?
Yeah. Okay, so I think I think that actually that's a great question, because it's a main motivation in our work. So yeah, as you just said, there are many works about trees or forest covers, but usually they are based on this FAO definition. So usually, for example, in world cover, maybe the class trees means trees higher than 5 meters or something like that. But it's hard to say what kind of forest inside this tree land cover. So you don't know if that's natural forest, if that's planted forest, if that's tree crops. So if you want to use that kind of land product for other applications, like support this EU deforestation regulation, then you just need one more validation step. And in our case, we just want to push forward in this direction. So we are trying to make this forest map in, just push it further, yeah.
Yeah, we'll move on. Okay, so the next presentation is full life cycle of Earth observation-based AI foundation models, lessons learned from real-world deployment by Zhang and Al, Allen Institute for Artificial Intelligence.
Yeah, thanks. So sorry I cannot make it in person, so I need to do this virtually. But yeah, hello everyone. I'm Yawen Zhang from Allen Institute for AI. Today, I will show our work on building and deploying AI foundation models for Earth observation, particularly what we have learned by deploying the models in real-world systems and where we are heading next. So for those unfamiliar, the Allen Institute for AI also called AI2, is a nonprofit AI research institute based in Seattle. We are founded by Paul Allen in 2014 with a mission to develop AI to address global challenges. A core part of our mission is the strong commitment to open science. So open source tools, datasets, and models, make them public available, is a top priority at AI2. So one of our core initiatives at AI2 is AI for the planet. So we have a large team working on this mission. Right now, AI2 has many ongoing projects focusing on AI for the planet, from maritime intelligence to wildfire risk assessment, forest monitoring, and wildlife protection. These are not just research works, they are real-world tools and systems used by conservationists, policymakers, and the local governments. We also have a climate modeling team working on long-term weather forecasting. The team generates high-resolution weather forecasting products that can be used in many different applications. So given the limited time today, I will focus on Skylight, our system for global-scale vessel detection, and how it led to deeper learnings that now guide our ongoing efforts. So for today's talk, I will start by walking through the full life cycle of building EO-based models using Skylight as an example. Then I will briefly show where we are headed next with a broader picture called the Earth System Platform and a new foundation model called Helios. So what is Skylight? Skylight is a maritime intelligence platform that uses AI to monitor maritime activity and support transparency at seas. It ingests the data from multiple satellites and provides actionable insights to maritime enforcement agencies, NGOs, and also governments. This tool has already been used by hundreds of organizations worldwide. So what makes Skylight powerful is the combination of scale, performance, and efficiency. Our models work across WIRS, Sentinel-1, Sentinel-2, and the Landsat. The images on the left show the satellite ships and the detected vessels from each of the Skylight satellite model, which covers different geolocation and times. Skylight model can run on low-resource hardware with near real-time latency. They also achieve high accuracy and cover all the exclusive economic zones. Our models are also highly reliable with 99.99% uptime. Also, everything is open source, including our dataset, models, and also the APIs. So from the Skylight project, what we learned is that no single satellite could capture the full picture, and combining different sensors like light, optical, and radar give us the most complete view of maritime activity. So we are also working on planning to expand to NISA satellite once it's launched, which can provide the SAR images, another very unique perspective on maritime activity. We would like to connect with folks working on NISA and explore ways to further collaborate. So here is a short demo of Skylight. And in this platform, you can select vessel detection event and then choose what kind of sensors you would like to see. Here we select optical sensors, including Sentinel-2, Landsat, and commercial images. With each of the detection, you can see the corresponding satellite image, and you can give feedback to the detection result. Some of the vessels are broadcasting their locations and metadata, so we record them with another model called Esa-Nasa. So I have added a link on this slide. The paper has been accepted by ICR workshop as a spotlight, and also the model has been open sourced. So feel free to check it out. So now let's dive deep into the full development cycle of the Skylight vessel detection models. And I would like to use Landsat as an example. So this chart captures our full model development loop, from sampling and labeling data, training models, evaluating the models, and finally deploying them in production. So for the Landsat model, we collect in total 18,000 vessel labels and applied a pre-trained swing transformers for vessel detection. Basically, the multi-channel Landsat images are being tokenized, and the first RCN head has been added for this object detection task. Our initial model has an F1 score of nearly 79% offline. So this process sounds straightforward, But actually, there's many lessons we learned from this. The first lesson is offline performance doesn't guarantee online success. Although our V0 model has good F1 score offline, but in production, we found so many false positives, like clouds, icebergs, whitecaps, and even some small islands are being mistakenly detected as vessels. So later, we addressed this issue by introducing a classifier trained with both vessel and false positive examples to further reduce the errors. In this two-stage model, the detector detects vessel-like objects, and the classifiers prompts the detection result to get the true vessels. And also, besides the F1 score getting from the holdout validation set, we also ask domain experts to evaluate the detection result directly, which helps us to understand the model performance better. And this led to our V1 model, which achieves better performance with 88% accuracy by human expert evaluation at a much lower false positive rates. So this model has been successfully deployed in the Skylight platform. So from the Landsat example, you can see that the real-world model lifecycle is often non-linear, especially for remote sensing models. We often have to revisit earlier steps, like labeling more samples, to address the issues encountered in deployment. It often requires several iterations to get things right. However, to reduce the back-end force and to speed up model development, here are a few things that we learned. First, successful model development requires diverse expert-level training samples. It also requires comprehensive evaluation across real-world scenarios. It is always helpful to evaluate remote sensing models across time and space to get a better understanding of its real-world performance. And finally, by getting user feedback after the deployment, we can just continuously improve the model performance. In addition to the model development, we also learned important lessons about the model deployment. So one of the big takeaways is that bridging the gap between research and engineering is critical to speed up the model into production. So it's not just about the model, it's about how you deliver it, which requires tight collaboration between the research and engineering teams. So for reliable ML model deployment, we summarize some of the key practices that we are following. For example, we build a model version control to track changes and enable rollbacks. We also run scenario tests to make sure that the model is doing a good job at each different cases. So for the Landsat example, we test if the model can distinguish between vessels and false positives like icebergs, cloud, whitecaps before model integration. Also, to make sure that the model can be easily deployed, we wrap the model in a fast API container so it can run as a microservice next to the rest of the pipeline. So previously, we directly share the model configuration and weights with the engineering team, but it was really hard to integrate to their existing pipeline. Switching to this model as API approach made integration much easier and significantly speed up the model deployment. So the lessons we learned didn't just help Skylight, they also shaped how we are doing other projects within AI2. So more importantly, it motivated us to think how to apply these best practices to more projects and applications, whether it's assessing wildfire risk, monitor forest loss, or mapping marine infrastructure. So we are thinking, can we have a unified platform and infrastructure that supports a variety of applications, build ML solutions for the task, and always apply the best research and engineering practices to them? So this brings us to what's next. So the next for us is the Earth System Platform, which we call the ESP. So we are building this unified infrastructure for Earth observation. Our ESP platform brings together multimodal satellite images, climate data, GPS, and other data sources. It offers models, tools, and interfaces for a range of Earth observation applications. While modeling individual datasets is valuable, there are many real-world tasks like crop yield forecasting or energy potential analysis that benefit more from combining multiple data sources. Our ESP is designed to provide support for both cases It makes it easy to integrate diverse data sources and models through shared infrastructure and toolings, which truly unlock the power of multimodal Earth observation data. So ESP is more than just a foundation model. It's a full-stack AI platform. Here's just a quick overview. First, it handles data acquisition and processing through the ES-LEARN. And the labeling and fine-tuning are done in the ES Studio. We also have a model zoom, which offers highly performant ES foundation models. For deployment, ESP provides both historical and real-time APIs, as well as embedding services. Finally, we have the ES Viewer, which supports visualization and also user feedbacks, so that partners can easily interact with our system. ESP is also designed to be developer-friendly, and we will open source everything, including the models and the tools, so that other people can easily use and contribute. We have already been working on a wide range of applications using our foundation model called Helios. So what is Helios? Helios is our Earth foundation model, built on earlier work from our team, mainly the satellites and Galileo models. So Helios tokenizes multimodal data, including Sentinel-1, Sentinel-2, Landsat, elevation, OpenStreetMap, and other modalities, and feed the tokens into a transformer model for self-supervised pre-training. This model is trained on globally diverse samples using multimodal, multi-resolution inputs. It has multiple model sizes, from very tiny to base to 1B. It also has great flexibility in terms of the input image size and the patch size. You can input either image or even a single pixel to the model. Helios supports a wide range of tasks, including classification, segmentation, change detection, and object detection, and on both single image and image time series. So besides evaluating our Helios foundation model on existing benchmarks, we also apply the model to many real-world tasks, like forest loss monitoring, crop type mapping, ecosystem mapping, and more, which helps us better understand the model performance in the real world. There is a lot more to come. We are scaling up model sizes, modalities, and also applications. If you are interested in what we are doing or want to use either our foundation models or any ESP-like components for your user cases, feel free to reach out to us. Thank you so much for your time. I'm happy to take questions.
Thanks.
Hey, thank you very much for your presentation. I've got two. One is the curiosity, and the other one is, I think, of interest to anyone. In terms of object detection, what type of decoder are you using?
Yeah, we are right now consider two types of decoder because originally, as for the satellites pre-trained, there's this like a fast RCA like had been added for the object detection, but for the like vanilla like transformer, we think maybe it's more helpful to use jitter or other like more like effective like object detection head. Yeah, so we're still exploring which is the proper head for that task.
Okay, and what about Helios? When can we expect to, have it online and people can use it?
Yeah, thanks for the interest. Yeah, we're still like, I think we have some estimation about the release date, which could be something in the summer. So yeah, hopefully we will have more information to give to the community. Yeah, so.
Soon to come. Okay, thanks. Any last question? No? Okay. Thank you very much again. Thank you very much to all the speakers. It was a great couple of sessions around benchmarking data sets and evaluating foundation models. And I believe there is a break now. Perfect. Thank you. Bye.